Hello, welcome. Today we're going to do a lesson on similar figures and scale factor. Sorry I'm not able to be there again today. Um, I will be in school tomorrow. So we're going to do this lesson by video. I want you to turn to page 29 in your packet. Hopefully Mr. Calistro can pause the video for a few minutes and let you work on this problem and see if you guys can find the missing side if these figures are similar rectangles. All right, hopefully you guys are done with this problem. And there are multiple ways that you could set this up. You could match the 2 up with the x, so you could say 2 over x is going to equal 7 over 10. Now, some people wouldn't do this. They would do like 7 over 2 is equal to 10 over x, or 2 over 7 equals x over 10. All of those are legitimate ways of solving this problem. But once the goal is we set up some proportion, and now we cross multiply. 7 times x is 7x, and then 2 times 10 is 20. Now we divide both sides by 7, and I have to break out my calculator for this. We know it's a little bit less than 3, so it'd be 2.857. So x is 2.8, let's round it to 6. And that's what we have. So what I wanted you to remember here, this is way back from first semester, or maybe the beginning of the semester. It was a few chapters back. Uh, if we have similar figures, if we have the sides, we set up a proportion to solve for the missing side. Now we're going to do the same thing today, but we're going to do it with area. And it's a little bit different, a little bit, less intuitive. So our goal for today is that we can use scale factors in different dimensions to solve for missing measurements in similar figures. And then you could identify the scale factor for length and area of similar figures. And then you can explain the relationship between scale factors of areas. Hopefully this will make sense in 10 minutes. And we have our success criteria. So first off, if I asked you how much bigger is this rectangle than the rectangle on our left, there's a few different ways you can think about it. You can, when you say how much bigger, like are we talking about the sides? Are we talking about the area? It's hard to think about how what bigger means because it could mean different things. We have to be a little bit more specific. So maybe what we could have asked is what's the scale factor for the sides and what's the scale factor for the area? So if we look at our next slide, our scale factor for their sides are 2 to 4 or 6 to 12. Both of these scale factors can reduce down to 1 to 2. So you could easily say that it's 2 times bigger. This rectangle is 2 times bigger. All right, that makes a little bit of sense. This is called the scale factor for the sides. We have a scale factor for the sides to be multiplying by 2, or a 1 to 2 factor. So our method would be to pick corresponding sides in the two figures and see what we multiply by 1 to get to the other. All right. Now, if we want to think a little bit more about these, on like how much bigger this is, uh, let's look at the perimeters. Let's see how a perimeter is, the ratio between the perimeter is. So if this is 2, since there's a rectangle, that's 2 and 6. So that'd be 8 plus 8. This perimeter would be 16. Now this perimeter, we have 4 and 12, so we'd have 4 and 12 here. And this perimeter would be 32. So our ratio of the perimeters would be 16 to 32, which is again 1 to 2. Now let's look at the area. Let's see if it has that same ratio. If I find the area here, 2 times 6 is 12 centimeters squared. So I'll fill it in here. And over here, 4 times 12 is 48 centimeters squared, so that's our area. Now, if I was in class, I would make you think about what is the relationship between 12 and 48, and hopefully you would see that that's a 1 to 4 ratio. Interesting. This is different than the perimeter. So, well, that's not lined up, but, oh. So the scale factors are of the sides were 2 to 1, the perimeters were 2 to 1, and scale factors of areas is 4 to 1. Now, a way to think about why it's 4 to 1, if I take one of these, that's one box up there, and see how there's 4 of them that fit inside of the big one? So that explains why it's 4 to 1 rather than 2 to 1. But if you go along the sides, you can fit 2 along each side, 2 up. All right. Now this one gets a little trickier. So the scale factor for the sides is 18 to 6. Now if I break 18 to 6 down, I get 3 to 1. Now, if you think about what the relationship was back here, what relationship did you see between the ratio of sides and ratio of perimeters? Hopefully you saw that they were the same. So the scale factor for the perimeters, we could do 18 plus 18 plus 18 and get that number, 6 plus 6 plus 6. So 18 plus 18 plus 18 is 54. And now if I reduce that, I can divide both sides by 18, and I also get 3 to 1. But now we got to think about the scale factor of the areas. How many of these things can I fit in here? And it's obviously more than 3. I can fit 3 along each side. So if I draw it in, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we line that up, we have 3 to 1, 3 to 1, and 9 to 1. So now what's the relationship between the ratio of sides and perimeters? Hopefully you see that they're the same. The ratio of the sides and the ratio of areas, 3 squared is 9, 1 squared is 1. So you have to square those. So these are our big properties. These are the things that kind of the main goal of the day that you guys come away with this lesson having this down. So the scale factor for the sides is equal to the scale factor for the perimeters. And if we want to find the scale factor for the areas, we have to square that scale factor for the sides, or scale factor for the perimeters since they're the same. All right. Hopefully everybody has that down in their notes so we can solve some problems. So when I start problems like this, it says find the scale factor for the sides. So I'm going to do SF sides, and then scale factor for the perimeters, and scale factor for the areas. Now, we don't know exactly what the perimeter is going to be because we don't know these sides, but we know the scale factor for the sides is going to be 12 to 15. And I'm writing it over here because we can simplify. We can take a 3 out of each of those, so that would be 4 to 5. And so the scale factor for the sides, 4 to 5. And we know the scale factor for the perimeters is the same. That was the property we just learned, so that's going to be 4 to 5. And the scale factor for areas, we just have to square that. So that would be 16 to 25. Now, I want to be clear about something. There's a little misconception that people get. The difference between a scale factor and what the actual length is. So this is not saying that this area is 16 and this area is, 25. Hopefully you're notice my error. This is not, it could be 16, but it's probably not 16. And this is probably not 25, but the ratio for every 16 units that are here, there's going to be 25 units squared here. And hopefully that'll make more sense as we go along. All right. Now, here we have the ratio of the areas from this big one to the small one. So I'm actually going to take this and I'm going to copy it and bring it over here because these 3 things I'm going to use a lot. So I might as well put them together, right? So we have the scale factor for the areas, 400 to 64. Now, I like before I do anything is to reduce this. I can take a 20 or a 8 out of both of those. So I can take 400 divided by 8 to get 50. 64 divided by 8 gets me down to 8. Now we can keep going here. I can take a 2 out of both, so I have 25 to 4. And I think that's as far as we can go. So I'm just gonna, yeah, well, I can leave it there. I was gonna erase it, but I'll let you see the work. So 24 to 5 is my ratio for areas. How would I go back to the ratio of perimeters and sides? Well, these are the same. We have to square these numbers to get here, so we have to square root to go backwards. So both of these have a ratio of 5 to 2. Hopefully that made sense, because we're square rooting these to get the ratio scale factor for the sides and areas and perimeters. Now we want to find this side. So we have to decide which scale factor we use, the side, perimeter, or area. It seems almost silly to say. Since we have a side, we use the scale factor for the sides. So I'd have 40 over x. Since the bigger one is on top, I'm going to put the bigger one here on top. So that's going to be 50 over 2, or 5 over 2, sorry. So when I cross multiply, 5 times x, 2 times 40 is going to be 80. And I divide by 5, and so that's going to be 1, and 30 is going to be 16. So that's going to be 16 millimeters. And there you go. That's our value for x. Let's try another one. Now, if we look at this, do we have a scale factor for areas or scale factor for sides? Hopefully you're seeing scale factor for sides, and that's 6 to 8. What I can take out of both those is 2, so that's going to be 3 to 4. So scale factor for perimeters, it's going to be the same, 3 to 4. Scale factor for areas, I square both those, so 9 to 16. Now here, we want to find the area. So since we're finding area, we have to use this ratio. So I'm going to say 9 over 16 is going to equal. Now this 13.5 is in the smaller triangle. The smaller number is on top. So I'm going to say 13.5 over x. And now we cross multiply. 16 times 13.5 to 16 equals 9x. And then divide by 9. And x equals 24. And that's it. The area of this green one is going to be 24 square feet. All right. Hopefully that's making sense. Let's try this one. The area of a regular octagon is 35 square feet. What is the area of a regular octagon with 1/3 of the length of the sides? We know the ratio of sides is 1 to 3. Oops. 1 to 3, because 1/3 the length. So the ratio of areas is going to have to be 1 to 9. We just have to square those. So what is the area of the octagon with side lengths 1/3 of the sides of the larger octagon? So this is the larger octagon. So if I have 1 over 9, 35 represents the big one. So that's going to go on the same level as the 9. Put this over x. And when I cross multiply, I have 35 divided by 9. And so x is 3.8 repeating. Square feet. All right, now this one, you could have probably done without this lesson. Uh, an 8x8 square cake sells at the grocery store for $6.99. They also sell a 9x9 cake for $7.99. Why is that second one a better deal? Well, the first one has 64 square inches, probably, uh, for $6.99. So when we divide $6.99 divided by 64, that's 0.109, so about 11 cents per square inch. So if we want to do the other one, we have a 9x9 cake that's 81 square inches for $7.99. And so if we divide that out, $7.99 divided by 81, and that's 0.0986 cents per square inch. So you can just say why. By how much? Oh, so you do 0.019, 0.109, I should say, minus 0.0986. It's a better deal by about a cent. How much? About 0.01 per square inch. Now, so you'll be losing a penny per square inch. That's not too bad, but you can see that one is a better deal than the other. All right, hopefully this makes sense and you can finish up the homework associated with this. Thank you.